ladies and gentlemen. We are now going to talk about Type 3 projectile motion, differing elevations. Basically put, instead of launching and landing at the same height, we are going to launch and land at different heights. Maybe it's going to be higher, or maybe it'll be lower. And what we're going to see is that much like with the previous two examples, each one of these sort of builds on the other. What do I mean by that? Well, when we started, we did a horizontally launched projectile. So we had, say, a person on top of a cliff, and they'd launch something forward, and it would come down and fall like this. Here we go, we'll put our person. Then we introduced type 2, and in a type 2 question, the person was standing, they could still be standing on the cliff, and they launch it, and it comes up, and then it comes down to the same height. And what we see is that if I cut this part off like this, and if I erase this beginning, this is the same basic plan as this, right? The arc remains the same. It's basically doing the same thing. So the only part that a type 2 really added was this whole rising to the top. Well, a type 3 is much the same. A type 3 is going to look very, very similar to a type 1, but with one extra step. For example, the question in our notes involves a blank where you could fill in your own again. I'm going to use myself again because, why not? The blank here says that on a 50-meter cliff, so we're going to say that Mr. C is standing on a 50-meter cliff, and he's going to launch a stick of dynamite because we're going to be a nice, wholesome physics class with fire and explosions. And I throw that stick of dynamite up, and then it comes down, like so. So when I launch it up into the air, it's going to have some kind of an initial velocity, and it's going to be going upward at an angle. Now, the numbers I originally chose for this was 20 meters per second at 25 degrees elevated from the horizontal. So this is going to be 25 degrees, and this is going to be 20 meters per second. And that's it. That's all the information that we have. So question 1 is going to be, how long is the dynamite in the air? How long is the flight, we could say? Okay, well, just like every other one of these examples, we got to break it into x and y. We've got to figure out what the horizontal component is, and we got to figure out what the vertical component is. Just like all those other examples, we're going to collect our information. VI, VF, A, D, T. We always need the same basic info. The question is just, what numbers do we have? Well, to get the horizontal and the vertical, we're going to need our trusty calculator, because we're going to need to convert this from two-dimensional to one-dimensional. So for this particular example, because we're dealing with an arc like this, right, we're going to be dealing with figuring out this one and this one. So far, this isn't any different than a type 2. And realistically, if I cover up, there we go. If that was the question, it just looked like this would be a type 2 question, just like the ones we did last time. But it's not, right? It's going to keep going. And that part is going to be tricky. But again, if I cover up like this, well, that just looks like a type 1 question, doesn't it? So these type 3 questions are very similar to a type 1 and a type 2 combined together. Just like how the type 2 question was sort of like twice the type 1, right? Because it was symmetric, so the falling part and the rising part were the same. So a lot of these things are all very similar. They're built off of the same basic foundation. But anyway, enough talking. Let's get some math in here. We've got, let's see, cosine of 25 times 20 is going to give us an 18. So this is going to be an 18.13. Then we're going to do the same thing with sine. Sine of 25 times 20. And that gives us an 8.45. All right, so let's get some units in there just to make sure that we're being as accurate as possible. And of course, this is going to go forward, so it's going to be positive, and this one is going to go up, so we're going to make that positive. Now, VF, we don't know what it is, at least not yet, but we do know that the acceleration is going to be negative 9.8 meters per second squared. The velocity final over here we know is going to be positive 18.13 meters per second because the acceleration is going to be 0. And after that, we kind of don't know a lot. Not really. Now, under normal circumstances, we're missing too much information. We can't solve this. Not easily, anyway. But what have we done every other time that we've had a problem that goes both up and down? We break it into two parts. So I'm just going to talk about y going up for right now. And in that case, this becomes 0 because at the top of the arc, like way up here, right about there, we're going to be pausing for just a brief second. Now, by making that 0, here's a key thing. The fall is not 50, right? The displacement here is not 50 yet because we're only talking about the part where we're going from the cliff edge up to the top, not here down. We're still going up. So that 50 doesn't come in yet. We don't know what the time is, but we do know that whatever the time is to get up is going to be the time it takes to go forward. Now, herein is the problem. Because this is broken into two parts, we have to take that into consideration. So just to be complete, I'm going to write down the y going down component as well. Initially, I'm going to start at 0. My final velocity, I don't know. My acceleration is going to be the same. Now my height. It's tempting to put 50 here, because I said the 50 doesn't count for going up. But think about it. When we go up, right, we started here 50 meters above the ground, and then we're going to go higher. And then from here onward, we're going to fall. And then from there onward falling, we're going to go farther than just 50, because we're slightly higher above the ground, right? This is where, as I said, if I cover up part of this, like this, boom, that looks like a type 2 question, so it's symmetric. But from this point onward is when things are new. That's the stuff we have to figure out. And there's a couple ways we can do it. We can try to figure out, cover all that up. We can try to figure out just this part that's now showing and then tack on this extra bit. Or we can just try to figure out everything going up to the top and then just work from there going down and figure all of that out. There's a couple different ways to do it. I'm going to show you one. So we're going to go with figuring out going up, and then we're going to figure out going down. And this isn't going to be 50. This is going to be 50 plus the displacement we took going up. And then finally, of course, the time, which we don't know. All right. This is a little more involved, obviously, than the type 2 and the type 1, but I think you're going to see that they're all very connected. They're all related. So let's start off simply. We have VI, we have VF, we have A. Let's solve for D. Let's solve for T. Okay, we'll start with that. So D equals, we've got VF and VI, we got A, let's use equation 4, not equation 5. So for equation 4, right, we're going to get VF squared equals VI squared plus 2AD. VF is 0, that makes it easy. VI is 8.45, and it's going to be squared minus 2 times 9.8, the minus, of course, coming from the 9.8, and then the D, which we're looking for. We get out our trusty calculator, we square, and then we divide it by 2 and 9.8. We're going to get that D is equal to 3.65 meters. So what is this telling us? It's telling us that we're going to go 3.65 meters up into the air. So from here to here, right, from the height where I originally was upward, we go an extra 3.65 meters. So here is where we do a little bit of the magic here, right? This is going to be plus an extra 3.65 meters, which means that the total height I have to fall isn't going to be 50. It's going to be 53. 3.65 meters, right? Because I'm going to fall from here down to the floor. And that, of course, is a little bit further. So we have to account for that. We have to include it. Now, I mean, the 3.65 meters isn't a lot compared to 50, so it's not going to have that big of an effect, but it's still something that we need to consider. So as like usual, we're calculating our values, and then we're propagating those calculations through in order to make sense of everything. So let's continue to take a look at this. We've got our D now. We can now figure out the T to get up to that halfway point, to get up to the top of the arc. We can use any equation. I'm going to use equation 2 because it's pretty easy. VI plus AT. VF is 0. VI is 8.45 plus 9.8. It's negative, of course. I should have put a negative in there. Let's just make that easier. Negative times time, which we don't know. So I'm going to take my 8.54, divide it by 9.8 equals time equals 0.86 seconds. So it's 0.86 seconds to get halfway up. Halfway. All right. We've got to figure out the rest, though, because the question originally asked us, how long is the flight? Not how long is the flight to the top, right? We're not figuring out how long does it take to get up to there. We're asking how long does it take to get to the entire thing until I hit the ground. So I have to take it just a little bit further. Now, on the plus side, I actually have a lot of information, right? I know how far I have to fall. I know the acceleration. I know the initial velocity. I just need to find the time. So that's d, a, and vi. Well, that's equation 5. So I'm just going to pull out equation 5 here. We're going to go d equals vit plus at squared over 2. The d is 53.65. The vi, 0, so that all goes to 0. That's very convenient. Minus 9.8 t squared over 2. This will be minus 2 because we're falling. Of course, we're going down. So we're going to do a little bit of math here. We're going to get 53.65 times 2 divided by 9.8, and then we're going to square root all of that. And we're going to get the time here is 3.31 seconds. So this is 3.31 seconds. So the original question, what is the total flight time? The total time is equal to the time to go up plus the time to come down. And this is the big addition of type 2, or type 3, I should say, sorry, is just that there's a lot of extra steps because things are no longer so simple. I can't just take the shortcuts that I did in the type 2, where I just calculate halfway and then multiply it by 2 just to get to the end. I can't do that because this type of problem isn't symmetric. That makes things annoying. So on the plus side, the whole calculating the rise to maximum height that we got over here, that part's the same. So this whole first half of the question remains the same. And the second half of the question is just a type 1 question where my initial height was just a little bit taller. Oh, right there. So really, it's like the first half of a type 2 attached to the second half of the second half, which is a type 1. Right, so we did a type 2 question to start with for this part. Cover that up. Type 2 question for this part here. And then for the rest of it, we do a type 1 question. So a type 3 is really just the first 2 things we learned in this particular unit combined together. That's it. That's all we're trying to do. Well, we started filling in our numbers. Next question that we can ask. I've thrown this dynamite down. Is there somebody down there? And they want to catch it. I don't know why. Maybe they're daredevils. Maybe they're stuntmen. B. If, let's make it simple. Mr. C, you know, the other one, because there are 2 of us. If Mr. C, the other one, is 75 meters away from the base of the cliff, can he catch it? So I'm asking, if he's 75 meters away over here, is that where the dynamite will land? Well, the dynamite lands 75 meters away. Well, 75 meters from the base of the cliff, that's me asking for this number here. So we just got to find it, right? We just take this time and we move it over, and that's the total time of the flight, right? No, it's not the total time. We just found the total time. It's right there. So this time isn't related just to the time of the rise, but the time of the fall as well. So both of these two go into making this time. On the plus side, the first part of this question already let us find it. So it's 4.17 seconds. Now we just have to solve. We're looking for d. So d is equal to VIT plus AT squared over 2. This becomes 0 because there is no acceleration. D equals 18.13 times 4.17. We plug that in. We're going to get d is equal to 75.6 meters. So technically it will sail just past him. Whoops, I guess he'll miss. So can he catch it? Maybe if he jumps. So it's going to be 75.6 meters, so catch if jump. That makes things a little tricky. Oh, we can fill in that extra number here. You'll notice, just like usual, we're filling in everything one step at a time. We started off with an almost blank set of numbers, and now, filling this in as we go, we've almost managed to complete it. This is pretty standard, right? We tend to approach our questions with not enough information to start with, and then over time, we fill it in. There's only one thing we don't have now: final velocity. Guess what we got to solve? C. How did I frame it? What is the final velocity? Very simple. Okay, we know what we have to do. Down here at the bottom, the final velocity is going to be at some kind of an angle. That angle is going to be built off of the horizontal velocity, which hasn't changed the entire flight because we ignore air resistance, and the vertical velocity, which we have to find. Now, if this was a type 2 question, the vertical velocity launch and land would be the same because we just assume that's how this works, right? We assume it's symmetric, but it's only symmetric up to here. From this point onward, it's no longer symmetric. So we need to solve for VF. On the plus side, solving for VF is really simple. We have all the other numbers. We just have to do it. So given that we have any number, I can use any formula. I'm going to use number 2. VF equals VI plus AT. VF, don't know, that's what we want. VI, 0, that's very convenient, minus 9.8, and the total time that I'm in the air, 3.31. Sorry, not the total time I'm falling for. I don't really care about this part because, that's the rising. I could solve with that, but I don't need to, so I'm not going to. So I take my 9.8 times 3.31, and that's going to give me a VF equals to 32.44 meters per second. So this one over here is 32.44 meters per second. Down, of course, negative. Now I just have to solve my Pythagoras. So I've got 18.13 squared plus 32.44 squared, all square root, and that's going to give me my final resultant. So let's go for it. 18.13 squared plus 32.44 squared equals. This is going to give us a 37.16 meters per second. That is clearly different than the 20 meters per second that we started with. And it makes sense they're going to be different because over here, right, if I go from here to here, this would be symmetric. Here would also be at this exact spot that is exactly the same height that I launched it at. This would be 20 meters per second at a nice angle of 25 degrees because that's what I launched it at. And if this was symmetric, that's what I'd get. But it's not. I fall for further, so gravity has longer to accelerate me, to speed things up. It's going to move faster. Similar, it's not going to have the same angle. We're going to see that if we look at this, right? It's going to be 32.44 divided by 18.13. So we take our 32.44 divided by 18.13. Second function tan. And we're going to get 60 degrees below the horizontal or depressed. So there's the two pieces we need in order to get our final velocity. What is this showing us? Okay, we did a lot of one-dimensional kinematics here in order to calculate all of this. We filled in every part of our chart, and our chart, of course, is a little bit bigger because we have the up and the down. It's not the only way to solve it, but it's probably the most straightforward. Similar, we saw that this first part of the whole thing, right, covering up using the notes here, this first part is the same as we saw before. It's a rising problem. Honestly, it's almost like a one-dimensional free fall problem that we had from the first part of the unit. Then, this part here is just a type 1 projectile motion. It's falling down and forward at the same time from a height of, if you recall, 53.65 because we got 3 meters up during the first part of the question. And that's kind of it. It asks you to solve basic information about this whole thing, and the only real adjustment is that we fall for further, or perhaps we fall for less. Once you start putting these together, I think you're going to find that it all kind of clicks into place. Now, the notes do go into a little bit. It formalizes a few official rules, right? And just to briefly summarize, in case you haven't read them yet, it does say here, right, that the horizontal motion remains the same the entire time, just like every one of these other problems. The vertical motion is no longer symmetric. We saw that, right? It's symmetric to a point, this point right here, because that's when it's the same across. The rising to max height, this part here, that part's the same as we saw previously as well. So the only real change is the falling from here down. This part is now a type 1 question, bolted on to the first half of a type 2 question. So keep all that in mind as you work through the various problems. See what you can do, and I think I'm going to leave it there, and I will see you guys next time.